so we can get things started. And thank you all for being here again. Okay, so what we're going to do today is we're going to review resonance structures. And that's because the last time we did resonance structures, I felt like I moved through it pretty quickly. And I want to make sure you all are fully understanding resonance structures before we move on. All right. And so I'm going to try a different approach today about talking when I talk about resonance structures and see if this will make a little bit more sense for some of you all who are like, oh my God, I think he started losing me. And so the first thing is let's draw a molecule that has the potential for resonance. And I will draw the same one again. Good evening, everybody. I feel like we're like a class right now. You know, we're like a nice little family. We have to get together one day and have like pizza and something. All right, so here is a molecule that has resonance, and we are going to draw it in two different ways because I really, really want you all to see this. So since this lecture is really mostly about review, let's talk. Let's take a little bit of a step back. So first of all, I look at this molecule, and what I want to do is to first check to make sure that all my atoms have the charges that they're supposed to have, and they have the electrons that they're supposed to have, right? And all of that comes back to our understanding of the octet rule, and for hydrogen, it's the duet rule. So every bond represents 2 electrons, right? And so carbon and all the other atoms, except for hydrogen, always like to have 8. Okay, that's the goal. And if they have 8, then good. And then hydrogen likes to have access to 2. So let's just walk through this molecule to make sure I actually drew something that makes sense, right? And that all my charges are well represented and nothing's left off. So the hydrogen on the left here, right? This hydrogen has access to 2 electrons. You can see that it is making 1 bond. That's 2 electrons. That's good. All the other hydrogens also have 1 bond. They have 2 electrons. So we're all satisfied here. This is a good bond for those hydrogens. And then the carbon in the middle, this carbon here, is making 4 bonds. Those 4 bonds means that it has access to 8 electrons, right? That's good. Carbon wants 8. Let's look at this other carbon now to the right of that carbon. That one is also making 4 bonds, right? 1 bond to the carbon on its left, 1 bond to the oxygen on its right, and it's making 2 bonds to the oxygen and north, right? So it has 8 electrons. So there are 2 important things here, right? For carbon should have 8 electrons, but it should also be making 4 bonds. So both of those things are true. We're happy with carbon is happy. Then let's look at the oxygen up north. This oxygen has 8 electrons, 2 bonds, and 2 lone pairs, right? So that's 4 electrons to itself in the form of 2 lone pairs, and it's making 2 bonds to the carbon. This is consistent with the pattern that we expect for oxygen. When oxygen is neutral and has no charge, it's making 2 bonds, and it has 4 electrons or 2 lone pairs to itself. So this is a good neutral oxygen. Then let's look at this oxygen now. This oxygen has 8 electrons. It has 2 in the bond that it shares with carbon, and it has 6 electrons or 3 lone pairs to itself. Now, this is not a standard pattern for oxygen when it's neutral. Let's remind ourselves of the patterns. Carbon, when it's neutral, likes to make 4 bonds. Nitrogen, when it's neutral, likes to make 3 bonds, and it has a lone pair. Oxygen, when it's neutral, likes to make 2 bonds, and it has 2 lone pairs. Those 2 bonds can also be to the same atom. For example, they could have been to a carbon, right? That's still 2 bonds and 2 lone pairs, which is the example we have on the screen. And then an atom like fluorine likes to make 1 bond and 3 lone pairs. These are the patterns we consistently see, and hopefully over the past few weeks, you've gotten very accustomed to seeing and have appreciated. Now, I don't know how many new people are on the calls, so I'm making sure I'm going over this in case you didn't get this information or work through this with us in the past several weeks. All right. So now that we have that, let's look at the oxygen and explain why it has that negative charge, right? Whenever the oxygen isn't making its normal pattern, we can calculate its formal charge. As a matter of fact, we can always calculate the formal charge for any atom in a given molecule. So let's start off with the oxygen at the top, just because, we're practicing. The formal charge always starts off with the valence electrons for that atom. And in order to know the valence electrons, we have to look at the periodic table. And we literally count from left to right until we get to that atom. So if we count from left to right on the periodic table, by the time we get to oxygen, we should count 6. So oxygen has a valence of 6. So it's 6 minus the sticks. There are 2 sticks or bonds, and minus the number of electrons which it has to itself, which is 4. And that gives us a formal charge of 0. And that is why we don't have a charge written on that oxygen, because its formal charge is 0. That fits its natural bonding pattern, which is when it's 0. And so we knew that going in. This next one, now let's do the math. We have a valence of 6. It's still an oxygen. It has 1 stick or 1 bond, and it has 6 electrons to itself, which gives us a -1 charge. And that is why we have our -1 charge written next to that oxygen. Are we all caught up? We're feeling good? Okay. All right. Fantastic. Now let's get to the challenging part of this section. And this is the resonance structures. Let me erase everything I've drawn so far, because we're going to need a little bit of space to talk about resonance, okay? And I clearly can't find the erase button. So here we go. So let's erase all of that and let's talk about resonance, okay? So resonance. What is a resonance form? Once again, a resonance form is really showing where the electrons are in a different version of the molecule, okay? So here is our original version of the molecule. There are a lot of electrons in this molecule, and we know exactly where they are. Let's draw them in. There are 2 electrons in that bond. Remember, every bond represents 2 electrons. There are also 2 electrons in this bond. There are also 2 electrons in this bond, 2 in this bond, 2 in this bond, 2 here, and 2 there. And then all the other electrons that are not in bonds are actually drawn in, okay? So this is a very confusing picture. The electrons are already shown as lines, so we don't need to draw all the dots in, okay? But we do need to remember, and I'm going to leave this one over here as a reminder to you, that every time you see a bond, you need to think of that as 2 electrons. Are we good? Okay. So remember, I was trying to explain to you last time that a resonance structure just shows you where the electrons are currently. But the electrons can be fluid. They don't have to stay in one place. They can move through this molecule, and they can go from one place to the other place, potentially. Not every molecule or every set of bonds the electrons can move through, but in many molecules, the electrons can move through the system. And the analogy I talked about is like your blood cells that are moving through your blood, right? So they're moving through constantly all through your body. If you took a snapshot at one time, a particular blood cell is going to be at a different part of your body than another point in time. And so the question is, can we move electrons throughout the molecule? No. To try to do that, you should typically start, right, with, this is kind of my cheat sheet for students, is if I'm going to ask you to draw a resonance, I'm probably going to have you move electrons from a place of high electron density to a place of low electron density. Or I'm going to have you move electrons towards a place that is deficient, right? So in this molecule, it's very obvious that I have a negative charge on my oxygen, right? We just calculated the formal charge, which means it's negative, right? And that you can pretty much say is that oxygen is electron rich, right? It has a lot of electrons, extra electrons than it should have. And so what this means is that's a nice place to start moving electrons from and seeing if you can flow those extra electrons, that electron richness, and push it into the molecule into another place. Think of an atom that is negative as you think about hot potatoes, right? A very unstable situation. You want to share that heat with another part of your body so you can handle it. Okay. So let's move the electrons through the system. Now, how do you move electrons? The number one rule is you cannot just throw the electrons from one atom to another atom. Okay. They have to move through the network, which means they have to be shared. Okay. You have to share them from one atom to the next, and to the next, and to the next, and to the next. And so the oxygen over here, which is electron rich, is going to take it's one of the lone pairs it has. It has three lone pairs. The electrons travel in pairs. And what it's going to do is it's going to share them with its neighbor. Okay, now let me erase that circle. Let me actually use a colored arrow to show the movement. It's going to share them with its neighbor. Now, why did I draw the line to the middle? I drew the line to the middle because if you're sharing something, the things you're sharing must end up in between you and the person you're sharing, right? They can't end up on the person or by you. It needs to be in the middle. And if you look at where the carbon is and where the oxygen is, this is the middle, right? So I'm moving my electrons from permanent ownership by oxygen to a shared relationship with the carbon. So that's a motion, and a very common motion we will do of electrons in organic chemistry. And it's you always want to start there. If an atom has electrons, the most likely thing it's going to do is to share it with its neighbor, right? Sharing is caring. Now, you have to always think about the consequence of every action that you do. Why don't we draw those electrons now where they will be? Those electrons will no longer, right, be here. We're going to pretend they've moved. That's what I'm doing. You notice I lassoed them and moved them. They are now in between carbon and oxygen. This is a very important thing to think about, because if you put them in between carbon and that oxygen, you have now changed the total count on that carbon atom. The carbon had 8 electrons to begin with, and you are now giving it 2 more. Remember, the carbon can only accommodate 8. And so in order for you to give it these 2 electrons, the carbon has to make a tough decision. If I'm going to accept 2 electrons, I have to get rid of 2 that I currently own. It's 2 for 2. I can't hold more than 8. And so the only electrons you're allowed to release are electrons in a pi bond, a double bond. This carbon currently has multiple connections. It has a single bond, and it has a double bond. So it can only release electrons that it currently has that are double bond. And so what the carbon is going to say is, okay, oxygen, thank you for your 2 electrons. I appreciate them. And in order for me to take them, I'm going to take 2 of mine and I'm going to give them to the oxygen that's next to me. Okay. And that way I can accommodate 2. And so those 2 are now going to move up to there, and we're going to have a new situation. No, that oxygen is at the end of the molecule, right? The oxygen doesn't have anywhere else to put them. So that's kind of all you can do. So why don't we draw the outcome of that? So the outcome of that then would be this carbon is now double bonded to that oxygen. If you want to draw the electrons exactly where they were, you could say oops, you could say that these electrons are here and these electrons are still there. The two that I just moved, they are now in this bond. Why don't we draw them as a new colored bond just to emphasize the point. There are those two electrons, right? They were once up here. Let's put them up here in blue as well, right? They were here, and now they are in between, and we draw that as a bond. That oxygen, carbon now has only one bond to the oxygen it was connected to. And those electrons, right, here are the two that it had originally. And then those two electrons that were in the bond are now on that oxygen instead of in between. And I'm trying to kind of change the color here so I can make you really see how they're moving through the system. That's where those two were, right? And so everything else remained the same. Nothing else was moved, okay? And so now we have a negative charge on that oxygen on the top because that oxygen now has an extra pair of electrons. If you look at these two molecules are different, right? For just looking at them as is, they look different. And what's different is the negative charge is now on a totally different atom. It was first on this oxygen over here. And now the negative, it was on this oxygen up here. And now the negative charge is on that oxygen. So you can think about it, right? We can draw kind of like a motion. The electron density is moving from here up to here. And then it's swinging back from there down to there, right? So it's swinging back right down to there. So it's a constant motion. That's what a resonance structure is showing you, is that sometimes the electrons are on one atom, sometimes they're on the other atom. And they can just move back and forth, back and forth, back and forth within the molecule. And both of these structures represent really the full molecule. It's giving you an idea of the fluidity of the molecule. Those electrons are not stagnant. They're moving back and forth, back and forth, back and forth. And so you have a better sense of the motion of the electrons in the molecules. All right, let's try one more. And then you're on the hook for this one. And then I'm going to have you, we're going to move on to something else. So here is, let's write atoms. This is an H. This is an H. This is a C. This is a H. This is an H. And this has a lone pair of electrons. So the first thing we're going to do is I want you all to look at this molecule. And I want you to tell me, okay, if there is a charge missing on any of those atoms. This is the molecule as is. Let's look through and see if there's a charge missing on any of those atoms. Some of you are quick. I mean, this is very impressive. You guys, I feel like a proud parent. You all are already giving me answers. Yes, that's correct. There's a positive charge on the carbon atom. And that's because if we calculate the 4-mole charge, we have 4 minus 3 bonds, which is plus 1. The carbon only has 3 bonds, 3 sticks, and its valence is 4. Remember, if you don't know the valence, you can look at the periodic table and count from left to right until you get that atom, and that will tell you the valence. Nitrogen, its valence is 5, and that is minus 3 bonds minus 2 electrons, that is 0. That's why we don't have a charge. So this is the molecule, okay? And on your exam on Saturday or this weekend, I'm gonna have you calculate this, okay? To make sure you're constantly looking at everything that's drawn and putting in charges if they are needed. Okay, so with that said, I want you to think through how we could draw a resonance structure for this molecule. Where are we going to start? This is different. I'm giving you 2 different scenarios. Remember, I told you, if you have a molecule that has a negative charge, that is something, someplace you want to start. Okay. When you want to move electrons through the system, you want to start with an atom that has a negative charge, if given an atom with a negative charge. In this molecule, is there an atom with a negative charge? There is not an atom with a negative charge. Okay. And so you're going to have to think about this differently. So the difference is, instead of thinking about the negative charge, you can see if there's a positive charge. If there's a positive charge, that tells me where I need to end up. So I'm trying to draw arrows so electrons end up onto that atom or being shared with that atom, so that atom can get 2 more electrons and relieve its deficiency. So where do I have electrons in this molecule? Remember also, the only electrons you move, and I'll point it out here, here are the rules. You should only move lone pairs and double bond electrons, okay? Those are the only things we can move. So do I see lone pairs or double bonds in this molecule? Yes, yes, Star, I see you online. You're killing this. You're like my A student. So I do see lone pairs on the nitrogen. So I can move those lone pairs. And what can I do with electrons? Can I give them away, or do I have to share them? I have to share them. So let's share them with my neighbor. Which neighbor am I going to share them with? Clearly the carbon, right? And so I'm going to take these and I'm going to share them. Remember, when you share, you have to share in between, right? Don't be greedy. It's not yours. It's sharing. Keep it in between, right? So I'm moving them in between. But when I move them in between, that now becomes a bond. 2 electrons in between that are shared is a bond. And so if I redraw that now, okay, now I have, and I'm done, right? Because carbon wants electrons, so I don't need to do anything else. If I share with the carbon's just going to accept. The carbon doesn't need to do anything to accept it. It doesn't need to release a bond because it's deficient. It's like, I just need 2, so I don't need to give up anything to get those 2. And so what that means is now I have 2 bonds between the nitrogen and the carbon, okay? And my carbon still has all of its other connections. Nitrogen still has all of its connections. Remember, we're only moving electrons, not atoms. The atoms need to stay exactly where they are. And so now we've moved electrons. Let's check to see if this leads to a charge. Is that carbon, does that carbon have a charge now? I think that carbon is good because the carbon is making 4 bonds. That's what it wanted to make to begin with. Does that nitrogen have a charge? Nitrogen normally has 5 minus 4 sticks, and that's it. So that's a +1. The nitrogen has a plus charge. And now you can see this is consistent with what? Yeah, remember, the math is always trying to find the formal charge. If you look at the periodic table, hydrogen is 1, right? Helium has 2. Lithium is 1. If you keep going across, you get 1, 2, 3, 4, 5, 6, 7, and you can put all the atoms in: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon is 8, right? So this is where we're getting these numbers from. And we had come up with a formula to calculate the charge, where this is the valence number. This never changes. And the charge is valence minus the sticks minus the dots. And whatever you get is the charge, right? So this math is in a previous lecture. I have it on YouTube. I think it's lecture 2. You can re-look at that. Yes, you can always use the periodic table to help you. As a matter of fact, in this lecture, you should always just have a periodic table. You should always just have one pulled up, and you can just count from left to right. Good question, Angie. You can move, you can do many, many moves. I'm keeping it very simple for you. Do you want to see an example where you do a lot of moves? Yes. Okay. Look at you all. You're all trying to be really, really good students. Um, let me erase this and I'll show you one with a lot of moves. So if you want to see something with a lot of moves, I can give you something like this. I'm not drawing the C's because that's gonna take really, really long to draw the C's. So I could have something like this with a positive charge on my oxygen, and I could have a nitrogen over here with a lone pair. Everybody sees that? This is a molecule, right? Remember, every point is a C. I'm just not drawing the C's out right now. And you have to know how many atoms are attached to it because of its connections. So let's draw arrows. I'm going to start. This is a positive oxygen. I have electrons here. Let's see. I could move these in between. Okay. And then that causes this carbon to have too many because remember, this carbon must have an H. If I don't have a charge, that carbon must have an H. All right. Carbon must make 4 bonds. That carbon must make 4 bonds. If I don't have a charge, it's making 4 bonds. And if I don't show what it's connected to, it's an H. Okay? All right. So here we go. We'd move that there. And then this would have to move over to accommodate that. Then this would have to move over to accommodate that. And then this would have to move onto the oxygen to accommodate that. So that is an example of you moving electrons through the system from one atom to sharing here, moving the sharing to the next atom, moving the sharing to the next atom until you get to an atom that can accommodate it. Now, I saw a question on the screen that was asking me, why is it that oxygen has a positive charge, although it has 8 electrons? Having 8 electrons doesn't mean that you're neutral. This is why we do the math to calculate the formal charge. The formal charge really is a calculation that compares how many electrons the atom owns currently compared to how many it owns when it's by itself. Oxygen always has 6 when it's by itself, okay? 6 electrons, that's what the valence is, right? But right now, oxygen only owns 5 in this situation that we have over here. And the reason why it only owns 5 in this situation is because it's sharing 6 of those with some other atom. Let's write a C over here. If you're sharing 6, you only own 3 of those 6. And it has 2 more. That's 5. So you're only owning 5 in this scenario. So 6 minus 5 is you're down 1, right? So you're really, the charge has nothing to do with whether it has access. Access is different from ownership, and we have to be able to appreciate that. Being surrounded by 8 electrons doesn't mean you own 8 electrons. And that's what this math is doing. This math is helping us to look at the ownership, right? So when we say access, we have to differentiate that from ownership. So right now, the oxygen has access to 8. So let's write that. It has access to 8, but it only owns 5, okay? And it should own 6 of the 8 that it's sharing. So that's what that calculation is, okay? All right, you all had a lot of questions. So hopefully this makes sense to you all. Is it making sense? All right, let's move on to the next page. So this is a new topic, and after this, we're gonna try to do some problems. Okay, so what happens now when you have 2 resonance structures? Okay, and you're like, which one is better? We call this the highest contributing resonance form. Okay, so for example, we have 2 resonance structures. Which one of them contributes to the picture of the molecule more? Remember, we said the electrons are moving back and forth, back and forth, back and forth between the 2 forms. But sometimes electrons can linger in one place, you know, it lingers a little bit longer on one atom, and then it slowly goes back to the other, then it lingers on the other one. So we're trying to see where the electrons lingering more. Is there one that it likes to be more like than the other? Okay. And so we have some rules to figure that out. And so you need to first draw your two structures, or three, however many. We're going to stick with two for our purposes. And then we're going to compare them. Why don't we use the example we did on the page before? So here was one structure that I gave you. Okay. It was this one. And it had a positive, and this had the lone pair. And here is the other form of the molecule, the same molecule, where the electrons moved in between the carbon and the nitrogen to give you a positive charge on the nitrogen, right? Everybody can appreciate these. These are the two resonance forms, right? We drew the second one, electrons are in a different place. So the question is, which one of those molecules or those forms of the same molecule do the electrons like to be in better, right? That's the question we're trying to ask. When I draw a resonance structure, is there one of them that the molecule is like, I like to be like this better than I like to be like that? And how you do it is, number one, the first thing you want to check is you want to determine if all the atoms have access to 8 electrons. Because if they have access, not ownership now, we're not talking about ownership, access. If they have access to 8 electrons, then that's good. Every atom wants access to 8. Whether it owns them or not, it just wants access. It'd rather own them, but it'd rather access over deficiency. So if I look on the left, the nitrogen has access to 8, but the carbon has access to 6. If I look on the sorry, that's on the left. If I look on the right, the nitrogen has access to 8, and the carbon also has access to 8. So because of that, this is the better one. The molecule is going to like to be in that form better than it would like to be in the form on the left. Does that make sense to everyone? So that's the first rule, is we're looking for access, okay? For the atoms to have an octet, okay? I see a no on the board. Does that make sense? Do I need to explain again? Do we have that? Okay. Star, it really isn't about it being a stronger bond. You could say it's a stronger bond because you have 2 bonds. Yes, you have 2 bonds compared to 1 bond. So that's definitely going to be stronger. Okay, so the next one is, what if you draw 2 molecules now, okay? And both of them have the same, have access to 8. All the atoms have access to 8. How do you distinguish them now, right? How do you distinguish them? All right, so I'm going to draw you an example when that's a case where that's an example where that's the case. So here is a molecule, okay? And why don't we try to draw a resonance structure? I love this one. People are going to get tricked up on this. Let's see. You notice in this example, there's no positive and there's no negative. Do we notice that? There are no positives and there are no negatives. So how do you draw a resonance structure when there's no positive and no negative? I didn't give you this as an example because this one is harder, because you kind of have to have a little bit of an intuition of where to start. But we do know, right, that you can only move, when you want to move electrons through a system, you can only move lone pairs, those are the dots, or you can move double bonds, okay? So you really only have a few options to start. You can start here, you can start here, or you can start there, right? Those are the only places you could start, okay? So which one do you want to start? Anybody has an idea? Where do you want to start? Remember, when you start, you got to share. All right, someone says O to N. You want to go that direction. I'm glad you say that first. Let's check that out and see if that works. So if I share this, right, we have to share, right? Everybody agrees? We have to share with the carbon. If I shear that, then that gives the carbon too many electrons, right? Everybody agrees? Because that's going to make another bond here. And that's going to have that carbon is going to have 10. So if I do that, don't I have to break something? Yes, I have to break one of the bonds. What kind of bonds are we allowed to break when we do resonance? Double bonds. Do we have any double bonds to break from the carbon? No, we don't have a double bond. A double bond is two bonds. We don't have a double bond. You cannot break the bond that you're just creating. You cannot break a bond in the same area that you're just creating a bond. You have to break a bond in a future direction. You have single bonds here, and you have a single bond here to that carbon. Okay? So because you cannot break a single bond, you cannot do the first bond. You can't do the first bond. Everything has to happen at the same time. You can only move the electrons if you can push them through the system. And so because of that, that direction is not possible. Okay? If you you cannot break the O to C bond because you're shearing in that region. If you're shearing that region, you're just shearing in that region. You can't move electrons from the same region you're shearing, unfortunately. Okay, let's go the other direction. Let's start from nitrogen. I can shear from the nitrogen in between the carbon. Yes, we can do that. And that works because now the carbon will have another bond, but the carbon has a pi bond or a double bond. It can break away from itself in a further direction. So this one actually works, right? So this is really the trick of it all, right? Is to remember that you have to have a future double bond to break in order to draw a resonance. So here, let's draw it. Let's draw the answer. This one is hard, as I told you all. It's a little bit harder because you have to think about all the possible options of where you can start and where you might end up. That takes a little bit more sophistication. Don't be mad if you don't get that yet. So now we have these two. You notice I put charges on those atoms. And yes, Anastasia, there's a little bit of gut feeling that comes along with it. You notice I put my charges. If you went through and calculated, you would have recognized that. Always calculate your charges, your potential formal charges on every atom you draw, right? You want to make sure you're not missing anything, right? And so I know when an atom has a charge because I'm so comfortable drawing them. Whenever I see nitrogen with 4 bonds, I know it's positive. Whenever I see oxygen with 1 bond and 3 lone pairs, I know it's negative. I just know that from practice. But remember, you can always calculate it, right? And so that's what we would have. So this is a good example of 2 resonance forms. So this is when we will check them. They all have 8 electrons. I'm pretty sure if you go through, all of the non-hydrogen atoms have 8 electrons in both of these structures. One on the left of the arrow and the one on the right. So the first rule doesn't apply. So what is the second rule saying? The second rule is saying that you need the molecule that has the fewer charges, right? You don't want any charge in your molecule. If you can avoid having any charges at all, that's better than having charges. And so if you look at the one on the left, there are no charges. Everything is neutral and everything is happy, right? It doesn't have a charge. But the one on the right, the oxygen is negative. The nitrogen is positive. That means the molecule is neutral, right? The 1 minus and the 1 plus will cancel out to 0. But it still has a minus and a plus. You don't want to have the molecule with a high area of electron density and a high area of efficiency. It's just better if there's no charge. And so because of that, we're going to like the one on the left, okay? Now, Jasmine, I see you ask a question if there's a charge on the carbons. None of the carbons have a charge in either configuration because carbon makes 4 bonds when it's neutral, right? Remember that? And if you don't remember, you can calculate it. It's 4 is carbon's valence minus the sticks, which is 4 sticks, 4 bonds, and that's all it has. There's no electrons, that's 0. And if you look on you miscounted the sticks, sorry. And if you look on the right, it's also 0. Okay, so that is what's going on here. Does this make sense to you all as the rules that we can follow to figure out? Yeah. Oh, of course. At what point would a chargeless molecule want to become charged? Believe it or not, this exists in your body, right? This molecule prefers to be charged. If you look at your DNA backbone, your DNA backbone has a lot of these bonds that are these exact bonds that I draw here. And believe it or not, it prefers to be more like the charged version than the neutral one. And that's in your body right now. So there are occasions when it really does prefer to be like the other, although that might not be very obvious to you. But by itself, it would probably prefer to be like we have it drawn here. Okay. All right. And then the final one now is consider the atom that has the charge. You have to think about which atom has the charge. So let's look at it. What if they all have 8 and they all have the same number of formal charges? You want to look at which one has the charge. Let's look at something like this again. I'm just going to modify this, and I'm going to write a negative nitrogen here. So now I'm giving you a negative nitrogen. So you all know where to start. Can you all draw me the resonance for this? Let me see you practice that. I have a negative nitrogen. And can you all tell me why my nitrogen is negative? I'm like pushing you all with to practice this. What's the valence for nitrogen? Valence is 5 minus 2 sticks. How many dots? 4 dots. So that is -1, right? So that's why it's -1. Remember, you got to practice this and get accustomed to that. All right, so draw me a resonance structure. I gave you something that has a negative charge, so you should be able to do this. You know where you need to start. By the way, drawing resonance is a very, very difficult concept for students. So if you actually get this, you are literally well on your way. Like a lot of students, it takes them weeks, months. Some students never get this idea of how to move electrons through the system in really a methodical way, like I'm explaining to you, and you all seem to be getting. So if you get this, this is not a simple concept for someone who's not taken organic chemistry before. If this is new to you and you're getting this, this is a major, major concept. Okay, so I hear people saying from N to O. That's correct. The nitrogen is negative, so it's going to share with the carbon. But if I share it with the carbon, I cause the carbon to take on too many electrons. And so the carbon has to release 2 to that oxygen. And that is going to be how it handles that. And if we draw that, then our carbon now will be double bonded to the nitrogen. The nitrogen will still have a bond to H, and it'll still have one of its lone pairs. And then the bond to oxygen now will be negative. I mean, oxygen will be negative because you'll get 2 more electrons. Are people, is this starting to make sense? If this is starting to make sense, you're literally slaying this. Okay, so let's go through the first 2 rules. And when you do this, it's nice to do it in order, okay? So let's go through the first rule. Determine if all atoms have a filled octet. Do all the atoms in these 2 molecules have a filled octet? Yes. None of them are lacking 8. They all have access to 8. If we count all the electrons around them, they all have access to 8. Good. Are there too many charges in one over the other? No, right? The one on the left only have a solo negative charge on the end, right? And the one on the right has a solo negative charge on the oxygen. So if you look at all the charges, there's just one negative on the left and there's just one negative on the right. So there's no difference in their charges. Does that make sense? So we can't use the second rule. And this is where the third rule comes in. The third rule comes in when you've done the first 2 and you cannot figure it out. And you're going to look at the atom that has the charge. And for our purposes, we're going to stick with negative charges. So look at the atom that has the charge. We have an oxygen that has the charge on the right, and we have a nitrogen that has the charge on the left. Okay? So the question is, which one do you prefer to have the charge? And MJ, I'll answer your question shortly. Which one do you think would you prefer to have the charge? I hear people saying the oxygen. That's correct. And why? Why the oxygen? Because the oxygen is more electronegative. Electronegativity increases from left to right on the periodic table. Oxygen is more to the right. It's more electronegative, which means it can handle the negative charge better. And so because of that, let's write that down here. Electronegativity. This is what we're using. The oxygen is more electronegative, and because it can handle that negative charge, we are going to pick the one on the right. And that's how we would do it. So you can walk through all of these three. Every time you draw a resonance structure, you might be able to, if it's drawn properly where you can make these decisions, you'll be able to decide which of the two is better than the other. Okay? Now, there are a bunch of questions. So what I'm going to do is pull up a periodic table just to really reiterate these points. Okay? Again, here is the formal charge. Okay? This is the pattern that you all need to know, right? If you see these charges, right, you understand. If you learn this table, you can understand when there is a charge and when there isn't a charge, right? This is what all of these atoms look like when they have a charge and when they don't. I've been emphasizing a lot to you all to remember this is the neutral situation, right? When boron makes 3 bonds, it's neutral. When carbon makes 4 bonds, it's neutral. Nitrogen 3 bonds, it's neutral with 1 lone pair, etc., etc. And then on the other side, you can see what they look like when they're positive, or you can see what they look like when they're negative. I have all of these memorized, but the whole point is you can always calculate this. We just walked through the calculation. All you need to know is the valence electron count for those atoms, and then you can go through and minus the sticks and minus the dots. Okay? Let's now talk about how you can figure out the valence electrons. If you have access to a periodic table, right, we go from left to right. Okay, hydrogen has 1 valence. Anything in this column, right, has 2. Anything over here is 3. Anything below this is 4, 5, 6, 7. Right? That's literally how we do it. Ignore this region for now, but you're just going across. And so if you have a picture of the periodic table, you don't need to actually to memorize these numbers. You can figure it out and then subtract the sticks and the dots. Does that make sense? By the way, the name of this document, all of these documents that I'm showing you here, you can find them on my website. My website is linked in my bio on my TikTok page that has all of the documents linked. Everything I use today and everything I've ever used, all of those materials can be found in folders and you can have access to that. Okay? So what I'm going to do now is I'm going to end there. I always go way more than I'm not ending for you all, but I'm always going way over than I have planned. Let's pull up a practice exam, because as I told you all, you have a test on this coming weekend. All right, so get those pens and those pencils out. We're gonna do 10 minutes of a little bit of a practice. Okay, and so you can find this file in the folder, right, for this week, the lecture for this week. But we're gonna draw. The first question is acid base. All right, let's do some beautiful, beautiful acid base. Remember now, the first thing you got to do is identify which one is the acid and which one is the base. By the way, before we start, let's look at this second molecule. What did I do here? Oftentimes, I will draw a molecule like this. What did I leave out on this that you know is there, that must be there? What did I leave out? The lone pairs, exactly. Do I have a charge written on these oxygens? I do not have a charge. If I don't have a charge, it means it's neutral. How many lone pairs must oxygen have when it's neutral? It must have 2 lone pairs, right? 2, so it gets access to 8. And this must also have 2 more lone pairs. I'm showing you this because oftentimes we don't add them because we can tell. We know what's supposed to be there and what's not supposed to be there based on our understanding of charges and neutral drawings, okay? So it eventually will become custom to this. So let's do the first one. Let's not do the second one. This is a practice. Let's do the first one, and then we'll jump to question 2 so we can get practice with these different types of questions. So let's do the first one. Which one is the acid and which one is the base? Remember, that's how we do these problems. Which one is the acid? Which one is the base? The one on the base is on the right. Beautiful. Acid is on the left. How did you know which one is which? How did you know which one was which? Negative charge on the base. Excellent. And the acid has a bond to a hydrogen that is weak because the sulfur is electronegative. It's on the right side of the periodic table. So that's a giveaway that that's going to be the acid because there's a weak bond that we can break. So you have 2 things to think about. So let us draw our mechanism. I need the arrows. Remember, we draw the arrows. How do we do the arrows? Can someone tell me? Where do I start my arrows from? Y'all are going to be good. No student's going to come in my class and not do well, okay? I know you guys got this. Or you folks. From the base. So we're going to draw the electrons from the base. And the base, it's going to share it with the hydrogen, right? And because it's shared with the hydrogen, what must the hydrogen do? The hydrogen must do what? The hydrogen has to, yes, it has to break. It has to give it up to the sulfur because hydrogen can only have 1 bond. So let's draw. You all are very good at the Bronsted acids. Let's draw our result. Sulfur is now going to have 1 extra lone pair. And if you calculate the formal charge, it's going to be negative. And what's going to happen is that sodium, which is a spectator ion, it just runs up to anything that's negative. It's like, hey, you're negative. Can I come sit? Right? So the sodium just going to run up to anything that's negative. It's going to just like attach itself there. All right. And let's draw what's on the other side. On the other side, now the nitrogen has 2 lone pairs, but not anymore. It shared 1 of those electrons with the hydrogen, right? And because it shared it with the hydrogen, it now is making a bond to the hydrogen. Okay, oops, I wrote sodium. Thank you very much for the correction. Can change my metal here. It is a lithium indeed. Thank you very much. I appreciate that. All right, hands up those who got this right. Hands up those who got this right. Beautiful. I see some, yes, me, yes, good, okay. Star, you are my star student. Okay, you can just, perfect. Yeah, you can't do your hand up. Okay, all right, let's try another type of problem. This one is a while back now, right? I'm bringing it all back. The test is gonna look just like this, by the way. I'm giving you a test. It's gonna look just like this. A 50%, we'll take that, okay? All right, so consider the molecular formula C8H8F2. So you have this molecular formula C8H8F2. Now, what you need to do, I asked you the first question. I'm kind of guiding you along, but I shouldn't have to ask you this, right? Because if you have a molecular formula and you want to draw something, which is what I'm asking you to do in B, you must always calculate your degrees of unsaturation. But I'm kind of walking you through. I know you all forgot the formula, so I'm just going to write it. It's the number of carbons. Let's write it in the color. The formula is the number of carbons plus 1 minus half of the number of hydrogens plus the number of halogens minus the number of nitrogens. And when we say halogens, halogens are really fluorine, chlorine, bromine, iodine, okay? That's what we mean by X. So if you have any of those atoms, you add the number of them. And if you have any nitrogen, you subtract it out. So let's calculate our degrees of unsaturation, or U. Let's calculate that. So everybody, oh wow, people already calculated. Are you sure you got 4? So we have 8 plus 1, that's 9, right? Minus half. How many hydrogens do we have? We have 8 hydrogens, and we have how many halogens? 2. And that gives you 4. Okay, yeah. No, this is good. 4 is right. That's 9 minus, let's do it. Let's do the short version. We have 9 minus 5, half of 10, and that's 4. I'm an organic chemist. I don't really think about math like that. So this is the only math we do, okay? Yes, everybody got 4? 8 plus 1 minus half of 8 plus 2. You're just filling in the numbers in those brackets, okay? And see what you get. So what does 4 mean? When we have 4, what does that number tell us? Anybody can remind me of what that number tells us again? 4 double bonds, or 4 rings, or 3 rings and 1 double bond, any combination, right? 1 degree is equals to 1 degree is equal to a ring or a double bond. But I kind of gave it away to you what to draw, because I then kind of directed you. I'm like, draw me one compound, right? The formula that I want you to draw is something that has a benzene ring in it, right? So let's draw a benzene ring. So if we were to draw a benzene ring, we would draw this. You should remember what a benzene ring looks like. We went through the functional groups. That's a benzene ring. And guess what? A benzene ring satisfies your 4, right? Because the benzene ring has 1 ring and it has 4 double bonds. So yay, perfect, right? So this is good, but we're not done yet, because we only drew how many carbons? 1, 2, 3, 4, 5, 6 carbons. This is our formula. We still have 2 more carbons to go, right? So you can draw whatever you want. You can draw a carbon coming off of here. You can draw another carbon coming off of there. You could put a fluorine up here. You could put a fluorine down there. And that would be an answer, right? Because you draw me a benzene ring and you still have your 8 carbons. Here they are, if you want to dot them. And you have your 2 fluorines. And if you don't believe me that it works out, you can put the hydrogens in, right? This carbon needs 1 more bond. This needs 1 more bond. This needs 3 more. This needs 3 more. And that's it. 8 hydrogens. So I never really check for my hydrogens, because it always works out, okay, if I do my carbons right, or my degrees of unsaturation right, okay? Or y'all remember this? It's coming back. You could have write it with the C's. I know some people are not that advanced yet. You could have written your double bond like this if you're still, like, I don't know how to do all of that stuff. You could have done that. That would be your double bond, right? With the different connections. And that would give it to you if you don't remember this. Okay. 1 more, and then we're going to wrap up. Yeah, you thought this was just a 1-page practice exam? Oh, no, this is a lot of practice exam. Come on, time to identify your functional groups. I want 4 functional groups. Let's go. 1 minute, 60 seconds. Functional groups. Yeah, I know you forgot the functional groups. Yes, you better go back to that folder. You better go back to that folder and dig them up, okay? Got a test this weekend. All right, everybody says carboxylic acid. I know y'all remember that one. You all love that one. Yes, that's a carb acid, right? Carb acid. That's our carboxylic acid. What else do we have? We have an amide. Oh, wow, look at you guys. You're so smart. Yes, we have an amide in this molecule. What else do we have here? Anybody? We have a ketone. Okay, all right. No, this y'all need to come to college. Y'all are ready. Ketone in this molecule, very nice. What else do we have? Yes, we have a benzene in this molecule. There's a benzene. You could also say you have a phenol. This is not a regular alcohol. This is a phenol, right? The phenol is when you have the OH on the benzene ring, okay? That's a phenol. Oops. You have the sheet with all the functional groups. That's a phenol. There is one more. Yes, Anastasia, there is one more, and I love it. You called it right. We have ourselves an ether. There we have an ether, an oxygen between two carbons. Anastasia, very nice. Oh, you guys make me so proud. Very impressed. Okay, so the last problem I had on this was a resonance structure, but in the interest of time, what you're going to do is you're going to practice this one. I'm going to write the answer key. I know I haven't put up the answer keys yet, but I'm going to spend tomorrow and write all of the answer keys and put this up. But this is your practice for this weekend's exam. To draw the resonance structure, I gave you a molecule, draw the resonance structure. And remember that each of those points are a carbon, right? So these are all carbon atoms. And you can fill out how many hydrogens they have, but draw the resonance structure. And then I want you to tell me which one is better, the original one that I gave you or the new one that you draw. And you're going to go through the rules like we just went through and determine which one you think is the better resonance structure. All right, today you guys really, really did well. Really proud of you all. Remember, for those who are new, I have everything linked on the website. All the documents are in there. I record all the lectures and post them on YouTube. So you can search me up on YouTube. It's Dr. Dre 4000 on YouTube. Or you can go on the website and you can find a link directly to the YouTube and all of the documents you need. I'm so excited. I don't know why I'm so happy, but this was really lovely today. Nice work, and I will see you all soon. I will not be there on Saturday. Sorry, I got plans on Saturday night. Saturday is your exam, so I'm going to just post it. And my expectation is you're going to go online, you're going to find the exam, you're going to do the exam, and then I'm going to post the answer key, and you're going to grade yourself. And on Tuesday, when we start, before we start a new topic, we're going to do a little revision, and you're going to do a little, share your results and so forth, and see what you all have. So thank you all very much, and I will see you soon.